Right, hi everybody, welcome back. This video is a response to a couple of you asking me to go back over sound waves. So my intention in this video is to use this as a revision tool, please. It's quite a small section in the syllabus. I want to go through it in general. I might miss out a few things that are actually on the syllabus, you know what I'm like. So what I did was I put the keywords directly from the syllabus above my head here. I won't go through them now, but when I get to the end of the video, I'll go back over those keywords and try to make sure I've covered all of them. But you can see them there now. Okay, so first of all, I just picked out some of the key things that are in the syllabus that you need to know about sound. Largely, it's just statements of fact that you need to remember. So first of all, the syllabus specifically says you need to know that the speed of sound in air is approximately 320 meters per second. Incidentally, that's about 1 million times slower than the speed of light. Secondly, you need to know that the speed of sound depends on the material that it's travelling through. Also, that means that sound can only travel through a medium. That medium could be solid, liquid, or gas, but sound can't move through a vacuum. You know that in space nobody can hear you scream. So it actually does state in the syllabus that you need a medium for sound to travel through. And like we've already said, the speed that the sound travels through that medium depends on the density of the medium. So the speed of sound in air is approximately 320 meters per second. In water, it's something like 1500 meters per second. It's faster through water because water has a higher density than gas. We go to even higher density materials through brick, approximately 4000 meters per second, and through metals like iron, several thousand meters per second. So for example, the speed of sound in iron, a piece of iron, is about 5,000 meters per second. Right, next, the human ear is able to hear frequencies of approximately 20 hertz up to approximately 20,000 hertz. That's not true of all humans. For example, I'm certainly older than you are, and as you get older, the receptors inside your ear become less capable of setting up signals to send to the brain. So I'm sure you can hear much higher frequencies than I can. Above 20,000 hertz, or 20,000 waves per second hitting your eardrum, we call that kind of sound ultrasound. And you know that you can have equipment that can send out ultrasound signals. It can bounce back, and you can turn those reflected signals into pictures. The really great thing about ultrasound, as opposed to X-rays or very high frequency electromagnetic waves, is that sound is not harmful. So you can use it for things like making a picture of a baby inside the mother's womb. Okay, so that's the basics of sound. If I move on again, this is a nice graphic of how sound actually moves. Now you should remember that sound is a longitudinal wave. It's pretty much the only longitudinal wave we see. All of the other waves we talk about are generally transverse waves. You need to know the definition of longitudinal wave, please. There's two things moving here. One, the movement of particles. Well, they're moving in that direction, backwards and forwards. And the movement of energy. Energy is moving from the guitar here to the ear in that direction. So what that means is that for this wave, the movement of vibration of particles is in the same plane as the movement of energy. It's the reverse for transverse waves. For a transverse wave, the particles will be moving at 90 degrees to the direction of movement of energy. Okay, so there's a bit of an optical illusion here. I don't know if you can see it. The red line here represents the guitar string vibrating, in this case, from left to right. You might think, or it looks as if the particles are heading off in this direction and heading to the ear from here to here and then hitting the ear. But that's an optical illusion. So home in, please, on maybe one particle in this general vicinity. And if you can just focus on one particle, you should be able to see it's not moving from the guitar to the ear, it's just vibrating around a fixed point. Now, what longitudinal waves don't have, that all the other waves we've seen have, they don't have crests and troughs. They have areas where the particles seem to come together, where they kind of packed, like here. That's called a compression, where the particles are compressed together. And then between the compressions, you see there are areas where the particles appear to be further apart. They're called Rho refractions. Very important to remember, please. I didn't put it on the keywords, but you should remember not crests and troughs, but compressions and Rho refractions. Okay. So these waves travel, in this case, through the air. The particles at this end cause the eardrum to vibrate, and that sets up the sound that we can hear. But it's important that no one particle travels from the guitar to the ear. Okay, I hope that was clear, that little animation. Okay, and then finally, I've just made a list of important things that we need to remember. Sound waves are longitudinal. Remember the definition, please. Sound travels through air at approximately 320 meters per second. We haven't mentioned this yet. The more the vibration of the particles from its fixed point, the bigger the amplitude. And amplitude equates to the loudness of the sound. The more an individual particle vibrates from its resting point, the louder the sound is. And then finally, the higher the frequency of the sound, in other words, the larger number of waves per second hitting your eardrum, the higher the pitch. So the highest pitch approximately that we can hear is about 20 kilohertz, which is about 20,000 sound waves hitting your ear per second. All right, I think I've covered everything. We've talked about longitudinal waves. We've talked about the range of human hearing. We've talked about sound above that level, above 20 kilohertz, which is referred to ultrasound, which can be quite useful. And then finally, I covered amplitude, which equates to loudness, and frequency of the wave, waves per second, which equates to the pitch of the sound, high pitch or low pitch. Now, to just finish this, what I can do is I can bring up on the screen a signal generator. And I'm going to try and play some sounds through my speakers as I'm recording this. It might not work. For one thing, I can hear my fridge quite loud over the top of this. So I'll try to distinguish the sound of my fridge from the sound of this signal generator. If you want to play with this at home, it's a free online signal generator, and this is the URL, Zinelski, I guess it is, .com/tone generator. Now what you can do is you can move this slider backwards and forwards, and you can set up a tone of a particular frequency. So I'm going to take it all the way down to, well, the minimum is 1 Hertz. I'll put the amplitude or the loudness up to 100% on here, and I will make sure my speakers are as loud as possible. Press play. Now I can't hear anything. 1 Hertz is below the kind of threshold of 20 Hertz. So let's take up to 20 Hertz. Well, I don't know about you, but I can't make anything out there. It might be that the settings on this tone generator in terms of amplitude are still pretty low in terms of loudness. Let's try 50 Hertz. No, I still can't make out anything there. Maybe you can. I'll take up to 100 Hertz approximately. Now I can just about make out a very low pitch sound there at 100 Hertz. I'll take up to 200. You can hear the pitch increasing, by the way. So that's a signal about 200 waves per second hitting your eardrum. Let's try some high pitch sounds, maybe up to 400. 600, that's getting quite annoying now. I can just about hear about 13,000 hertz, 13 kilohertz. And I certainly can't hear anything there at just above 20 kilohertz. Maybe you can, but I certainly can't. I'll stop that just in case it's very, very annoying. Okay, so that's pretty much all we need to know about sound. I hope it was helpful, and I will speak to you in our lesson this week. All right, take care, everybody.